Yeah, hello and welcome back. Today we're not just going to solve a normal calculus problem. We're going to do a hard one, like exercising a demon or something. This one is called Ahmed's integral, and this integral was from this was from an American mathematical scientist. Um this model appeared in 2002, and for years it has terrified undergraduates and delighted integration bees. It looks deceptively simple, but standard techniques like u-substitution and integration by parts will lead you into a maze of impossible algebra. To solve this, we have to think in higher dimensions. So firstly, let's start by the setup. If you try to substitute, let's just see the problem in front of us. 1 second. If we try to substitute this part, yeah, I think it's visible. This part, if we try to substitute this part, which is gonna be u equal to square root of x squared plus 2. Okay, yeah, so all of this is under the root. Okay, so if you will hit a wall immediately, that you will hit a wall immediately, because the x plus 1 is a term in the denominator, so it destroys any symmetry that you try to exploit. So we are going to use a powerful weapon like something called Feynman's trick. Okay, so it's a differentiation under the integral sign. Yeah, because we have the square root here in the denominator. So yeah, one more specificity to this case is the double integral substitution. So we will start off by doing tan inverse tan, or a tanh of arctan of a, which was the question, is going to be equal to an integral from 0 to 1 of a 1 plus a square y square dy. Okay, so this is our key. We will replace the arctan, this tan inverse tan of square root of this part, square root square x square plus 2. So this is the first part. This is our second part. So third part is going to be after we substitute that with our original problem, the integral differentiation, let a equal square root x square plus 2. Okay, so so it's gonna be tan inverse tan square inverse of square root x square plus 2 is going to be this one. It's going to become from 0 to 1 of square root x square plus 2 over 1 plus x square plus 2 y square by dy. Okay, so this is our third step. Our fourth step, let's change colors here. Now we are going to substitute this back to the I, the original question itself. Let's say this question was called I. Okay, let's name this I. So we are going to substitute this back to I. So it creates a double integral now. So our fourth step here is going to be that I is going now to become the integration from 0 to 1 of 1 over x plus 1 times square root x square plus 2 times the integration from 0 to 1 of square root x square plus 2 over 1 plus x square plus 2 y square dy, all by dx. Okay, we have just simply substituted this part. Okay, this part, we have substituted this part and this one. this one, inside our I in that part. Okay. So that leads us to the fourth point. Look what happens. The ugly, or let's not call it ugly, the one x square root x square plus 2 is going to become the numerator in the inner integral, and cancels perfectly with this, like this cancels with this. Let's change colors here. So this now cancels perfectly with this. Okay, so we are going to be left with let's say step 5 in the denominator and the outer integral. Okay, so the moment the problem cracks open to be I equal to integral of 0 to 1, second integral of 0 to 1, or double integral I mean, of 1 over x plus 2, x plus 1, this part, times 1 plus 2 y square plus x square y square, okay, all times dy by dx. Okay, so now this was let's name this like this is part 1, this is part 2, this is part 2, okay, and that was part 1, okay. And let's do now part 3. Now part 3. So in part 3 we can do the following. Okay, so now we have a double integral, and this double integral is by Fubini's theorem that we can swap the order of the integration. So let's say instead of doing dy by dx, let's integrate dx first. Okay, so let's rearrange the denominator in the the last part, this one. Okay, so it's gonna become I is going to be integration from 0 to 1 of integration of 0 to 1 of 1 x plus 1, yeah, x plus 1, this part, then 1 plus the second part, 1 plus 2y square plus 2 plus y square x square by dx, all by dy. Yeah, in the last step it was outside, yeah, but now we going to do the first dx first. Yeah, we have put it inside to do it first. Okay, yeah. Okay, so now let's focus on the inner integral, this part. Okay, this inner integral, we are integrating with respect to x, yeah, and treating y here as a constant, like it's like as if it was a, yeah, if it's a differentiation by x, yeah, integration by x, I mean, treating y as a constant. Sorry, the integrand is a rational function of x. This screams like partial fraction decomposition. Yeah, if you know partial fraction. Partial fraction is where, let's say we have x over some denominator here. It's going to become a plus b for these denominators, like, because we can't usually just separate denominators, we can separate numerators, like x plus y is can be x plus and y, yeah, but here we cannot do separation for denominator. Normally we use something called partial fractions. I guess most of us knows about this part, so we are going to solve instantly this part. So it's going to be 1 x plus 1 for 1 plus 2 y square plus y square x square equal to a over this part x plus 1, x plus 1 plus, okay, so this is of a second order. See, it's y square or it's x square, so it's going to be bx plus c, yeah, for it's the partial fraction of a second or of a higher order, yeah. 1 plus this part now, 1 plus 2y square y square x square, yeah. So now skipping the algebra of this part, we're gonna solve the coefficients a and b and c and find that beautiful decomposition. The inner integral splits into two manageable parts. After performing the dx integration from 0 to 1 in that part, we are left with a function of y. So the inner integration result is after the integration. Okay, so you can skip that part, or you can do it, try to do it by yourself. It's going to be simple. We're just going to do integration from 0 to 1 for dx. So it's going to become let's change colors here. Colors here are a little bit not too much, but let's try anyways. Len of 2 dot y square over 1 plus y square plus pi over 1 plus y square minus tan square tan inverse tan of 1 plus 2y square all under a root, and so on for our in practice, the symmetries are often used here to relate I in a simple integral j. A common intermediate step in Ahmed's solution derivative is the relationship. So let's just do the 2i, like this was for I after integration. So let's say now for 2i is going to become, for integration of from 0 to 1 pi to 1 plus y square dy minus integration from 0 to 1 of tan inverse of integration, of square root of y square plus 2, okay, by dy. For this integration part, it's going to become by dy, and for both integrations, since we did already the differentiation by x, integration by x, I mean. So, and this part is going to be written too much, so I'll just skip it by doing dots here. Okay, so now we notice that the second term is initially our original integral. This one has became originally our our initial integral. This one, this is I here. We are applying limits. We arrive the identity relating our integral I to known constants, and like that we can discover that our equation now is going to become I is going to equal pi over pi square after this integration, okay, pi over 16, and this part after integrating from 0 to 1 of this y from integration by dy is going to become pi square over 16, and this part we have said it's become I, so now our I has become I equal pi square over 16 minus I. Now our variation is depending on the exact decomposition path taken over involving the integral of, like, say tan inverse of y over square root of 2. So actually let's look at the standard symmetry result here, derived by Ghaffar Ahmed himself, or Zafar Ahmed. Utilized the substitution to the x himself. He have solved this the way like that. So x equal tan of theta, so, and carefully split the integral, proving that the integral is simply half a specific rectangular area, half a specific rectangular area in the inverse tangent plane. The algebra is going to just, let's simplify it to this state, like that we're gonna go on to this state, which is going to be I plus, let's say, correction term, let's say CT, and let's call it CT here, equal 5 pi square over 48. Okay, so the final result usually derived directly as like that. So they're usually derived as let's say times 2 here, so it's going to be it's going to become 5 pi square squared, this is 2, over 96. Yeah. So let's jump to the evaluated result. The messy logarithmic terms vanished or combined into constants improving or involving pi. The arctan sums or the inverse tan term sums up gracefully. So then the dust settles. The value of the hardest integral is a rational multiple of pi square to become that as our conclusion. It's going to become as I, or this the starting value, the starting question itself, this where I is equal to this, I is going to become now 5 pi square over 96. Yeah. And there it is, 5 pi square over 96, a number that feels surprisingly clean for such a chaotic start. We started with a square root inside arctans or inverse tan and ended up with a pure geometric constant. Yeah, it's geometric, it's a geometric constant here that is beautifully or this is the beauty of an advanced integration. Yeah, so would you like me to explain something else in another video? I would be happy to do that also. Please feel free to do comment or subscribe or like, and I will see you in the next video. And question off also in the comments if there is something not really that clear. Okay, yeah, and thank you very much for your time, and bye bye.